Okay, so I think today I'm just gonna make it like a review session. So if you have any questions, you could ask, and then I can go over it. So I still haven't gone over the new stuff like maximal, prime ideal, but I figured that like I don't think any of you would really care until after the midterm. So I think it's best if I just make this like a midterm last minute question type of session. So is there any question you want me to go over? Team 15. What's okay? So let's start there then. Yeah. And then we'll continue as we go. So show there is no non-zero ring homomorphism. Z mod 3Z to Z. Yeah, so you always have a ring homomorphism that just maps everything to zero. And you can easily check everything. Yeah. And like you can check everything works. Yeah. But that's like the trivial one. So instead, right, let's sort of, so Z mod 3Z is cyclic. So do you agree by the ring homomorphism property that all I need to do is tell you where I send one? Okay, so if I sent 1 to 0, this would be, I mean, I guess class of 1. This would be just the 0 homomorphism, right? Because if 1 gets sent to 0, 2, which is 1 plus 1, or if you like 2 times 1, is also sent to 0, right? And obviously 3 is sent to 0 as well, because 3 is 1 plus 1 plus 1. And 1 gets sent to 0. So if it's non-zero, if phi non-zero, this is sent to A where A is not 0. Do you all agree? Okay, but then where does 3 go? 3 is by ring homomorphism property, right? Phi of 1 plus 1 plus, so let's put equal, but phi of 1 class of 1, this is phi of class of 3, right? But this is by ring homomorphism property. It's this. This looks, I hate writing the brackets. It makes everything look very ugly. 1. Yeah, so this is A, so it's 3A, right? So phi of 3 goes to 3A, right? Another way to think of this is it's a ring homomorphism, right? So if it was, then 3 times 1 is the class of 3, right? And yeah, I guess that doesn't really help. I guess, yeah, you just need addition. So, but what is 3 in Z mod 3Z? Yeah, so in other words, this is saying 0 gets sent to 3A, right? But this can't happen. Yeah? Because if A is non-zero, 3A is non-zero. I mean, in the ring homomorphism, you must send 0 to 0. So yeah, it's not well defined. Uh, it's not phi of 3 is not well defined. I mean, phi of 3 is an element in Z. It's more you say the map phi is not defined, is not well defined. So yeah, phi not well defined. Uh, is everyone clear on this? Okay. So let me look. What's the other number? 14. Show that a finite ring with unity and no zero divisors is a division ring. So how'd it go? Okay. With unity and no zero divisors is division ring. Yes, so what do I need to show? I need to show every element is invertible, right? Okay, does everyone agree? Yeah, so from here, let me think. So finite ring, yes. Okay. So this is so what we're gonna do is we're gonna define a map. So the idea is when you take so define a map um given A, so let R be our finite ring with unity and no zero divisors. And we're gonna let A be an R, and this is like an you know arbitrary element, and we're gonna define a map from R to R, phi from R to R, given by A, I mean X, an element X in R goes to AX. Yeah, so this is phi sub A. Yeah, and first off, the idea is this permutes every element in R. Yeah, so what do I mean by permute? I mean that this is a what do you call it? You know, isomorphism. so so of course, when I do this, I mean in the multiplication operation. Yeah. So why is this? So before I continue, right? Injective is easy, right? So how do I show injective? I assume phi a of x is phi a of y, and then I want to show x is y, right? Does everyone agree with? I mean, this is the definition of injective, right? Yes. No. Okay. So let's just if I assume this, well, I know what the map does. This is ax is ay. Sorry, a non-zero. So I mean, so obviously, so yeah. So take an element a not zero, right? I mean, such an element exists because we sort of. I mean, if not, then R is the zero ring, and in the zero ring, I mean, every element non-zero is invertible because there's no any other element. There's just zero. So that's like the trivial case. So without loss of generality, we could assume A is not zero. Then why does this imply x equals y? Yeah, we have no zero divisors, right? So I could do ax minus ay is zero, right? Subtract on both sides. The distributive property of the ring tells me I could factor the a out. And I know a is not zero, and since there's no zero divisors, x minus y must be zero. So this is where we use this is where we use r has no zero divisors, right? It's injective. Now, why do I know it's surjective? It's so I'm claiming it's surjective because these two, yeah, they're finite, right? And they have the same order. R is finite, right? So whenever you have a map, forget like homomorphism, forget you map from like a set S to a set T, right? And like both of them are equal and they are less than they are finite, right? To show bijectivity, you just need to show injectivity or surjectivity, right? Because once you have one, you have the other. Does everyone agree with that? That's like set theory. Because how about this? If you're injective, right? How about this? Let me just convince you all. If you are injective, right? Every element in S goes to like a different element in T, right? So it's like, for example, this map is injective. So do you agree injective tells you that this is less than or equal to the cardinality of S is less than or equal to cardinality of T? Do you all see that? Right? And surjective is the other way, right? So surjective, you must hit every element in your set, right? In the image. So if you hit every element in the image, you must be at least bigger than your image, right? So this tells you this, right? Yeah, so you see why you only need one, right? Because once you have one, once you have injective, I know this is true, but I know these are equal. Yeah, so it can't be purely less than or equal. so so like that's the idea of like why you only need one of them. So and it's not only that they're equal, right? I mean, like, you need them to be finite, right? Like, if it's infinite, it's kind of hard to say, like, which ones, what type of, because there's like many types of infinities, right? There's like, I mean, you can think of it like inner this and this. This is like way bigger type of infinity, right? I'll just put it that way. Yeah. I mean, R is Z is infinite, R is infinite, but R is clearly like way bigger, right? So okay. Anyhow, once we have that, does anyone see why we're done? Phi A is surjective, right? So given arbitrary element B and R, right? The map phi A sends B to A dot B, right? This thing right here. Oh, sorry. I already put given an element A and R. So A was an arbitrary non-zero element, right? I could have done this for any arbitrary A. So in particular, since phi A is surjective, there exists X, I'll call it X prime, such that AX prime is like 1. Does everyone agree with this? It's surjective. So I must map to 1, right? I must hit every element in R, right? Because I am surjective. So in particular, I must hit 1. Yeah? But then this means that, X prime is A inverse. That's the sort of the idea. Yeah? And like A was arbitrary. So if you want to show another element was invertible, then obviously you just define the map. If you want to show another element A prime is invertible, define a map, phi A prime, and then do the same. Is everyone clear on this? So I guess the idea to take away, one thing to know is multiplication by element in R permutes elements in R. Like it just swaps them around. Yeah. How about that? Everyone clear on this? Okay. What other number? Huh? I need to check the chat. What was the last number? Or at least for now. 15. What is 15? Okay, so if you are nilpotent, if you raise to some power, you are 0. Prove that R has no nilpotents if and only if 0 is the only 0. Okay. Oh, this is just induction, I feel. Yeah, okay, so, yeah, so show R is nilpotent if and only if 0 is only 0 of, that sounds weird. 0 is only 0 of x squared. Yeah. So this way is clear. Yeah, it's by definition, because if you are nilpotent, if 0 was not only 0, right? Let a not equal to 0 be a 0 of x squared. Then a squared is 0, but that means a is nilpotent. Oh, is not. How about this? The English is bad. Has no nilpotents. How about that? So, but that means A is nilpotent, right? Just take n to be 2, right? So is this way clear for everyone? Like this is like easy. Okay. So now we assume basically if if something squares, so assume if something, so what does this mean? So this means assume if something squared is 0, 0 is only solution, right? So now, before I continue, what if let's work with powers of 2. Is this case clear if like n was a power? So assume there exists n such that a to the n is 0, right? We need to show a is 0, right? But my point is, if n was like a power of 2, is it clear why this is clear? Like this is, this thing is true. Like want to show a is 0. Like for example, if n was like 8, then a to the 8 is 0, right? But then a to the 8 is just a to the 4 squared, right? Now using this, right, I have something squared is 0, so 0 is the only solution, right? So using the blue underline, I know a to the 4th is 0. Yeah, because I mean a to the 4th is a solution, is a 0 of x squared. Yeah. So now, but then a to the 4th is a squared squared, and that's 0. So again, using the blue underline, a squared is 0, right? But then, of course, this means a is 0. Is everyone clear on this? Yes? No? So if you were a power of 2, you are done. And if not, you could just make it a power of 2, right? Like if n is 9, right? I know a to the 9 is 0. Then just multiply by a to the 7, both sides, right? Then I get a to the 16 is 0, because 0 times whatever is 0. And then a repeat argument, right? Just do the same argument, and you're going to get a is 0. So you're done. Yeah. So in like case 1, n is power of 2, right? You just do it by induction, right? So, follow this, right? You're going from a to the 2k is 0, but then that implies a to the 2, but a to the 2k is just a to the 2k minus 1, or how do I say this? Oh, sorry. 2 to the power of k. 2 to the power of k. So now I could, make it squared, right? A to the 2 to the k minus 1 squared is 0. But then, and then repeat, yeah? And then case 2 is n is not, then make it so, yeah? I mean, you can always multiply by some power of a to make it a power of 2, right? And then you go back to step 1. What do you mean by always legal? I mean, these two elements are equal, right? So all I'm saying is consider this term, right? But a9 is equal to 0, so this is 0. Because so this is on the other hand, since a9 is equal, I mean, since they are the same element, I'm just multiplying by the same element, right? I don't know how that's and then this is just exponent rule. Contrapositive. So you mean assume R has nilpotence, then I mean, if you assume R has no potence, then you know for all A and R, there exists NA. So N depends on A such that A to the NA is 0, right? So how are you going to show, 0 is not the only 0 of x squared? If you're doing contrapositive, you're showing if R has no potence, then 0 is not, then x squared has a 0 other than 0, right? I mean, it would be nice if yeah, I mean, in either case, you want to divide it to cases, right? Like, and then if and you're still doing the same thing. If n is odd, then yeah, you just multiply by another a, and then you're essentially doing the same thing. I mean, you have to split it to cases in either way. I don't see how it makes it easier. You would still have to do even odd, I guess. Yeah. Let me think. That should be complete. That should be very obvious, right? You had the theorem that said that said characteristic. What? Uh so I know fields have either characteristic 0 or p. I'm not sure about purely integral domains. There might be some weird stuff. No, but this should be easy, right? Because you had a theorem that basically said characteristic, it's only determined by how many multiples of 1 you add, right? So it doesn't matter if your subdomain has different, less elements as than your bigger domain, right? Because in either case they both have 1. and you only need to check it on 1. Uh, is that clear, Joy? I mean, if you add 1 n times, right? If the characteristic of the small one was bigger, right? Then if you add 1 n times, there's no reason why you would get right, unless it was 0 in the bigger one, because you're just, I mean, if it's a subdomain, it all the fact that it's a subdomain doesn't matter, because for characteristic you're just checking how many times you add 1, right? And they both have 1. So do you all know what theorem I'm talking about? uh I think, yeah, I think he wants you to just use that theorem and then be done with it. Let me try to find it. It's uh, where is it? uh Field of quotients. Anyhow, it's so subdomain is a subset that is also an integral domain, right? And in the definition of integral domain, it is a ring with unity, right? So subset that is integral domain. One 181, 182. Yeah, that's probably it. So yeah, so I'm talking about theorem 19.15 on page 182. Theorem. Yeah, you just use it like it doesn't matter if you're, if you consider a subset because you're just checking it on the element one and they both have one. So uh, so without this, it's a bit hard, right? Because subdomain, like you're checking the n could be smaller, right? Because or smaller slash bigger. I don't know which way it goes, but because you're considering less elements, right? But I mean, theorem 19.15 just says just check it on one. uh, any other questions on the? So just so you want, like, the midterm is like what, 9 hours span? Not the time, but I think it's like a 9 hour span or something. So I make sure you take it in time, like, and there's no quiz this week. Problem 1 part XVII. I don't think there's any dumb questions, but so how about this? Let me ask you, what do you think the answer is? So what do you think the answer is? So how about this? I'll tell you this. This is like a one line answer. So um, yeah. Well, it means like, it means this, right? So it means that, like, you know this is a ring, and it's saying that there's a field that has like Z mod HZ as a subring. Yeah. Yeah, exactly, Eric. Yeah, you're right. You're done. Right? A field cannot contain, because if it contains a set with zero divisors, that means the big thing itself has zero divisors, right? So the opposite is not true, right? Like, if maybe you have a big thing with zero divisors, but when you consider the small thing, right? The small thing could be like the stuff without zero divisors, right? So like, you know, I don't have an example top of my head, but that's certainly possible, right? If you imagine it. But but certainly if you have a small thing with zero divisors and a big thing that contains it, well, that big thing will still have zero divisors, right? So yeah. What are 2, 8? Oh, 8 is simple. Show p minus 1 factorial is congruent to 1 mod p. Yeah, okay. Is everyone clear on, p, is everyone clear that p is a prime? Yeah. So how about this? Let me ask you something. Given a group, so the group of units of z mod pz, is everyone convinced that this is just everything in p minus 1 factorial, right? It's p minus 1, p minus 2, all the way to 1, right? These are all the units in z quotient. Yeah, sorry, -1. You're right. Z quotient pz, right? And you know z quotient pz, the units, right? I'll call it cross, which means that they have inverse under multiply. I don't know how the book writes it, but this, and you showed in your quiz that this is a group, right? Everyone follow? Make sure you follow because the answer is like in like 2 sentences. So every element we can group it with its inverse, right? Can group with inverse. Right? So we could form pairs, right? Because it's a group, every element must have an inverse, right? We can group them into pairs. Does everyone follow? So group into pairs. Now, which one is not a pair? It's those that have its own inverse, right? In other words, if by own inverse I mean like the element itself is its own inverse. Yeah. So what you're going to see is if you group it, what element is its own inverse? Well, I know x. That just means I satisfy x squared is, you know, like 1, right? That means when you square it, so and you know over a field, this has only 2 solutions, and you know the 2 solutions. It's -1 and 1, right? So basically group like pair 1, like, you know, pair, here's a pair, right? And the only things that are not in a pair when I multiply everything is -1 and 1. Yeah. Now these pairs, they're inverses. So I get 1, I get 1, I get 1. And you're going to see it multiplies to -1. And that's your proof. So yeah, this is just a question on group theory, I guess. I mean, I guess it's ring theory because this you consider it a ring and then you consider the group of units inside of it. But this is like a group theory question. Yeah. Everyone clear on this? Okay. Any other questions? So it seems like you know, you're not really being tested on like the this week's stuff, right? I don't really see. Oh, I mean, I don't really see ideals aside problem 10. But I mean, like, other than that, like, you probably aren't being tested on like ideals that much. At least I don't see it from like, just looking at like just skimming over the questions. Like, it seems that aside problem 10, like, I mean, problem 10 is ideals, I feel. So, problem 10 is like certain, definitely on ideals. Uh, I mean, aside problem 10, yeah, I don't see any ideal questions. So maybe he didn't meant to give you problem 10 then if you told me there's no ideals. So uh, any other questions? So you have like 8 minutes. Through 10. Is that the one I talked about? Uh, okay, F a field. This is F. And phi from F to R is a ring homomorphism. Show kernel phi is 0 or F. Yeah. This is easy. So let me ask you, what are the ideals of F? Remember, ideals are stuff with magnet property, right? F is a field. Yeah, it's 0 or F, right? Look familiar? so, so we're almost done. So like, it's 0 or F, right? We can't have anything else because once we have a unit and we have the whole ring, right? Because if we have a non-zero element in F, right? I have the magnet property, so I can multiply by A inverse and 1. So now 1 is in my ideal. And once you have 1 in your ideal, you have every element in your ring, right? In this case, a field. So you're almost done. So your second step is show kernel phi is ideal. Kernel phi is ideal of F. Yeah. So what's kernel phi? It's the set of X in F such that phi of X is 0, right? Everyone agree? And at this point, you're just checking axioms. So like, let me just say magnet property. I think I did this in discussion, but let's do it again, right? Given R in F, X in kernel phi. I want to show Rx is in kernel phi, right? But this is easy because if X is in kernel phi, this means phi of X is 0, right? Now I want to show Rx is in kernel phi, so I want to show phi of Rx is 0, but phi is a ring homomorphism. So this is phi of R times phi of X. But like, I mean, this is, let me just say this is equal to, but I know phi of X is 0 and anything times 0 is 0. So So we're done with the magnet property, yeah? Rx is in kernel of phi. I mean, you could do the same for XR. And then it's a subgroup under addition because, well, if XY is in kernel phi, I need to show X plus Y is in kernel phi. But if this isn't, this just means phi of X is 0, phi of Y is 0, right? And I want to show phi of X plus Y is 0. But again, phi of X plus Y is phi of X plus phi of Y. And so that's 0 plus 0. So indeed it's 0. Yeah? So this is because phi is a ring homomorphism, right? And it has identity, right? It has the identity because we always know in a ring homomorphism, phi of 0 is 0, right? So 0 is certainly in kernel of phi. So we certainly have the identity element, the additive identity, right? And we have inverse. So if Y is in kernel of phi, right? That means phi of Y is 0. But then phi of negative Y, which is the additive inverse, is also in there because this is this is negative phi of Y. And that's negative 0, which is 0. Yeah. So you're done, right? We showed kernel of phi as an ideal of F, and the only ideals of F is 0 or the whole field, right? Everyone clear? Okay. Yeah, good luck on your midterm. So again, no quiz today, I think. In fact, I don't think you had a quiz yesterday either. So I think we just want you to study for the midterm for this week. Everyone good? You have like 3 minutes. 12. The only units are, yeah, it's the units of Z, right? And yes, it's going to be -1 and 1. Yeah, so if I were you, I would I mean, obviously at some point you're going to know how to do all these questions, but it's more like make sure you time yourself, right? Ask yourself how long it took you to solve each question and see if it is enough for the midterm. So if you looked at it the first time and you were to do it, how long would it take you? Were you able to solve it within the time limit, I guess? Or come close to, right? I'm pretty sure there's going to be partial credit. So okay, that's all. Well, I don't know how long it takes you to do your homework, so hopefully that's short amount of time. Okay. So yeah, good luck on your midterm. I will see you all maybe in my office hours later today, or if not, next week. All right. No problem.